Okay, let's just quickly think about what we've done because there's a few ideas that I want you to link and keep in your mind. So we've been solving this differential equation in the green box at the top of the page. What was important about this differential equation? Well, this is the Green's function equation. In physics, you'll always see a Green's function equation of this form, meaning linear operator acting on the Green's function is equal to minus I times the delta function. So it's always going to be a linear differential equation, linear in G, the Green's function, meaning there's no G squared and no G cubed terms. In addition, you'll often find that the Green's function is an equation with constant coefficients. And by that, I mean coefficients that are independent of x mu. In that case, there's a rather general method to solve this equation, and that's by using the Fourier transform. So we move to Fourier space. Now, just a comment. If the coefficients of your equation are not constants, then there aren't really good general methods, and you just have to struggle in solving the equation. So problems with constant coefficients are particularly nice because we have a general method to solve them. Okay, so how do we move to Fourier space? Well, we write down the Fourier representation for the Green's function. And when we did this, we used the fact that we've got translation invariance. So our Green's function is a function of x and y, actually only depends on x minus y. And we also wrote down the well-known Fourier representation for the delta function. Plugging these two into our differential equation, we got the second green box on the page, which means we mapped a problem in calculus to a problem in algebra. This was an extremely easy equation to solve. There's the solution inside the blue box. And then we could plug it back into our integral representation, our Fourier transform, and get the red box at the bottom of the page, which is the solution to our differential equation. Now, there's a few things about the solution that should be puzzling. So let me point them out. So what did we do? We mapped an algebraic we mapped an algebraic equation into a differential equation. Now, this looks suspect. And the reason why it looks suspect, well, let's first of all think on the algebra side. Okay? We had a times by our Green's function was equal to minus I. Well, we know exactly how to solve that. We just say G is equal to minus I over A. And that's exactly what we did. And I want to stress something now. I want to stress that this equation had a unique solution. Okay? So let's record that. Unique solution. On the calculus side, we were solving a differential equation. Well, when you want to solve a differential equation, that means you have to integrate. But whenever you integrate, there is an arbitrary constant of integration and arbitrary constant of integration. And what this means is there is no unique solution. So it looks a bit suspect that we've mapped a problem from algebra into a problem of calculus because the algebra equation has a unique solution, whereas the calculus equation doesn't. So I want to now just build on this idea, okay? And I want to go into this a little bit more to show you exactly where this non-uniqueness is coming from. So let's keep this differential equation. Let's take it downstairs. Okay, good. So there it is. And let's do something else. So there's my differential equation. Now, what I'm going to consider, I'm also going to consider the homogeneous problem. So I put an H onto the Green's function to denote the homogeneous problem. And the way that the homogeneous problem is defined, I just put a 0 on the right-hand side. And the second equation, the one for the homogeneous solution, it really does have non-trivial solutions. And this is the source of the non-uniqueness. You see, if you've got g of x comma y, and it's a good Green's function, then I'll come along with g primed of x comma y, and g primed is defined to be g of x comma y plus any constant times by the homogeneous solution. And if I now work out, well, what equation does g primed obey? Okay, so I'm just going to plug it into the differential equation, m squared on g primed. Well, you know that g primed is a linear operator. And because g primed is a linear operator, first it'll act on the first term in g, and then the operator will act on the second term in g. So we will have d dx mu, d dx mu plus m squared acting on g. That's the first term, then plus alpha, d dx mu, d dx mu plus m squared acting on the second term, this homogeneous solution term. And I've just taken the alpha out front. That's no problem. And when it acts on the first term, well, this we said was a valid solution to the Green's function equation. So this is just minus I delta 4, x minus y, plus, now the second term solves the homogeneous equation. So that's equal to 0. So we get plus nothing. So we see that g prime is also a solution. So here you see very explicitly that there is no unique solution. How would you usually find a unique solution? You get uniqueness by imposing something like boundary conditions, or maybe an initial value condition, or something like that, okay? But you have to impose some extra data, an initial condition, a boundary condition, or something like that, and that's the only way that you'll get uniqueness. So now we have a real problem. We've got a problem because we claim that we've mapped two problems into each other. The first problem has a unique solution. The second problem doesn't have a unique solution. So obviously something must be wrong. Where did we make a mistake? Well, if we go back to our algebra problem, this will have a unique solution as long as I can divide by a. So let's now rescue this equation, and let's now talk about this one. This is our algebraic equation. Okay. So when would this be solved? This is, oh, we can leave that green. This is solved uniquely as long as minus p naught squared plus p dot p plus m squared is not 0. But algebraic solution is not well defined if p naught is equal to plus or minus the square root of p dot p plus m squared. At these values of p naught, in fact, we cannot solve our algebraic equation straightforwardly because it has the form of naught times g of p is equal to minus I. And at these points, if you look at the integral solution that we had, it's points at which the denominator, p squared minus m squared, vanishes. When that denominator vanishes, the integral is singular, And if the integral is singular, we need to specify some extra data to get a unique solution. So as soon as the integral is singular, there are many ways of defining it, because we have to define how we will treat the singularities. And those different prescriptions for how we treat the singularities mean that we no longer have a unique solution, and different ways of treating the singularities corresponds to picking up different homogeneous solutions. So the non-uniqueness that we saw in the calculus problem is actually present in the algebraic problem. And it's precisely those points where to get a solution, we have to divide by 0. And this again is a very general statement about this method of solving for Green's functions. You'll always find that there are points that this algebraic equation can't be solved because you need to divide by 0, and those always correspond to defining the homogeneous contribution to the Green's function. So those are the ideas that I want you to connect in your mind. We're now going to talk about different ways in which we can define the integral.